welcome everybody to this webinar. I'm going to go ahead and introduce our speaker, and then we'll turn it over to him. We'll have a number of others joining us as well that are external. We're also recording this so that we can post it online as part of a webinar series on data analytics and process systems engineering. So anyway, thanks Aasim for being willing to come and join us today. Let me give a brief bio of Aasim. He spent 23 years in oil and gas process automation. He started out as an electrical and controls engineer and moved into HCI design, commissioning, project management, and finally into business management. He's been running businesses or business units in various companies since 2007. Currently, he's with a large service provider in the oil and gas industry, overseeing 2 business units and a new product development team. He's an electrical engineer, and during his career progression, he's done various business and technical courses, including MIT Sloan, Chicago Booth, UT Austin, University of Houston. He's PMI certified, TUV certified functional safety engineer, and ISA certified automation professional and cybersecurity fundamental specialist. And one of the things I really appreciate about Aasim, in addition to his vast experience in this area, he's currently doing a master's in data analytics from Georgia Tech. So his learning never stops, and he's continuing to continue to improve, continuing to learn at whatever stage he's in. All right, well, very good. Aasim, I'm going to go ahead and turn it over to you now for your presentation. And then along the way, I'll be monitoring the chat window just for any questions that come up. And if you're okay taking those questions as we go.
John, I'm perfectly fine with that. And thank you very much for saying that, because I cannot see the chat window for some reason. So if there is any question, I'd appreciate if you relay it to me. Thank you.
Okay, very good.
Thank you very much for that introduction also. I appreciate it. I was going to do that, but I'm really glad that you did it, because then I don't have to repeat all of that. So today, what I'm going to do is skip the quick intro, because John has already done that, and touch on 2 main topics. The first is going to be oil and gas value stream, the big picture. And by that, I mean that very often we talk about upstream or production or refineries, or even sometimes even components within refineries and these facilities. But we kind of miss the big picture of oil and gas. How does oil and gas production start, and where does it go to finally? And the whole infrastructure that makes it happen. So I'm going to spend some time, probably majority of the time there. And then at the end, or towards the end of the presentation, we'll talk about some examples where analytics may have good application on those oil and gas facilities. And then I'll leave some time at the end for Q&A as well. So like I said, I'm going to skip this slide, except for this one last thing that John actually touched on. But I was going to say that whatever you do, wherever you are in your career, always keep learning. It's important at any point in time, but I think the future that we are getting into, the need for learning and continuous learning is going to be humongous. We don't know where we will be and what kind of skill set will be needed in 5 years from now, let alone 10, 15, 20 years from now, when your careers are probably at your peak. So make it a habit, always keep learning and learn stuff that are maybe completely out of your area of comfort. The more you do it, the better you will be suited for the time to come. All right, so I call this a story of oil and gas, which is to say, and you'll see we'll build it up to where it is and where it finally ends up being. Before I move on, we've seen this picture or some semblance of this picture probably in many cases. First and foremost, I'd like to say that this is really the production aspect of it. There's the drilling phase, which is when the hole is drilled to the reservoir, completions, fracking, etc. But we're going to talk about today about the production phase only, which is when the Christmas tree is on and oil and gas are generally flowing. This is a picture that shows that. And it's a good picture, except that it's grossly out of scale. We all kind of know it, and it says, here's a Christmas tree, and that's a production line, and there's a reservoir. And it is a good picture because it shows a lot of good things. But I say it's grossly out of scale because this is how it is really. The wellhead is maybe about 6 feet. The reservoir is up to 40,000 feet under the ground. So if that line was scaled, even approximately, that Christmas tree will actually be just literally barely a pixel on that screen. The length of that production line is huge. The Christmas tree, like I said, there's a picture of it to give an idea. It's approximately the height of a human being. The depth can be anywhere from 5,000 feet to 40,000 feet. There used to be a time previously when wells were just about 3,000, 3,500 feet under the ground, but now we've used them all up. So now we have to go deeper and explore further down. The largest field, the reservoir, the little reservoir at the bottom there, that is usually multiple thousands of square miles or square kilometers. Just to give an idea, the largest oil field in Saudi Arabia with 100 billion barrels of oil is 4.2 thousand square miles, and many are even bigger. I put this in just to give you a perception of how things really are. And really, it's a marvel of science that we can sit right at the surface and drill down deep, 40,000 feet deep into the ground to get to oil and gas. So we are producing. Now the well is flowing, and we have the Christmas tree that's producing something. That something is water, gas, or oil, and in most cases, a combination of all. If it's just water, nobody likes that well, and even though it may be flowing water, in oil and gas industry, that well would still be considered a dry well. Dry meaning it doesn't have oil or gas, it's just water. If it produces just gas, actually there's always water. When I say just gas, I mean gas and water, but no oil. It's considered non-associated gas. It's still producing water. If it has a little bit of oil in it, it's called condensate. Also not the kind of well that we generally like these days. We are looking for oil. And when a well is producing oil, it's actually producing water and gas and oil. In this case, if it's producing gas, that gas is called associated gas, which means that it's associated with oil. And because there's water and we're looking for oil only, you'll probably come across this wording quite a bit. That's called water cut, which says how much of the total volume produced is water. Of course, the lesser the water cut, the better it is. But the statement of fact, unfortunately, is that for each barrel of oil that we produce, there are about 10 barrels of water produced. So 10 barrels to each barrel of oil, 10 times more water produced than oil. Similarly, another important KPI is gas to oil ratio. We would like for this to be as low as possible, which is to say, the more oil we can produce and the less gas, the better it is. It's defined as standard cubic feet of gas versus a barrel of oil. More than 10,000, and it's called considered a gas well. Less than 5 would be an oil well. Anywhere in between, it will be considered an oil and gas well. And it could be producing all of it. And of course, then we have to separate the oil and gas to make it work, which is what we're going to get into. And that's where the story actually really starts. So the combination of oil, gas, and water as it comes out of the well is called crude. Crude oil is what we've all heard of. The very first thing that we have to do as it comes out is separate all of them. So there's something called a separator, very simple vessel. You've probably studied some of it. It separates water and oil and gas. Water being the easiest, it's treated to some degree so that it doesn't have any oil or gas left in it. And it's either transported, re-injected back into the well, or reused in some other way. Oil is taken to some further processing and put into tanks for local storage right at the facility. And from those tanks, then either it can be railed out, as is the case in North Dakota, or it can be trucked out, as in the cases in many other facilities, or more and more commonly, it has a pipeline that takes it out. Now, these pipelines can be really long, and oil doesn't just flow. So in many cases, in most cases, we have pumping stations along the pipeline. These pumping stations just literally push the oil along. And given the profile of the pipeline, which is to say how high or low it goes as the profile of the land changes, it could be about 20, on average, 25 miles. Every 25 miles, we need a pumping station. If it's hilly, of course, we need more pumping. If it's flatter, then less pumping. But 25 miles, and the next pumping station will come up. Because we also don't want the pipeline to leak, and God forbid, if it leaks, we would like for the flow to stop. There are what we call block valves along the pipeline. These block valves, again, depending on the profile of the pipeline, can be 5 to 10 miles from each other. Of course, we would like for the distance to be shorter so that we can have smaller sections of pipeline that can be isolated, but 5 to 10 miles is a good estimate. At pumping station, there's generally plenty of processing as well as plenty of instrumentation. But even at something as simple as a block valve, which is literally just a valve that you can shut off, sometimes purely manually, sometimes electronically, sometimes even remotely. But there's generally pressure, temperature, and some more measurement taken, which is used later, and we'll get to that a little bit. What also happens is that given that pipelines are fairly long, a single pipeline may carry oil from multiple sources. So these are called laterals. And a single pipeline may be carrying oil from one particular facility, one customer, but in many cases, multiple facilities and multiple customers. So to make sure that everybody knows how much oil has been put into the pipeline by what customer, there's quite a bit of metering going on also. By metering, I mean how much oil is being put in by any given facility, any given customer, etc. So at the other end, as it's taken out, everybody knows how much was put in by customer X and how much is being taken out. I'm obviously showing only a couple of valves and a couple of metering stations, but there are many of those. To give an idea, if there was a pipeline that was a 1,000-mile long, of course, there's a pumping station every approximately 25 miles and a block valve every, let's say, 5 to 10 miles. So there are plenty of those along a typical pipeline and plenty of metering stations. So this pipeline, of course, ends up going into a refinery where the product is refined, and then the refined product, and that means the gasoline that we use in our cars, the diesel, the jet fuel, etc., that's shipped out, taken to a tank, or further distributed through some other means. Going over to the gas line, in many cases, there is a little bit of processing that goes on at the facility where it's produced before the gas, anything happens to gas. Multiple things can happen to gas as it leaves the facility. Unfortunately, flaring is common, not as common as it used to be, but it still happens lesser and lesser so now, but it can be flared. Or in some cases, it can be further processed and either re-injected or used for gas lift. These two are different terms, but what that means is that if there's plenty of gas available, that gas can be either put back into the reservoir, in which case it'll be considered gas injection, or it can be used to lift any production happening in the production line. So it's actually not injected into the reservoir, but actually injected into the production line, simply to increase the production of oil and gas, just like you would notice Coke would rise up faster if it had more bubbles. So it basically literally does that. Again, more commonly than that, the gas is also put in a pipeline and taken to a gas processing facility. Just like oil, gas also need to be pushed along. Because it's gas, that pushing is not needed as much. So there's a compressor station along the pipeline also, approximately every 50 miles or so. The difference between pumping station and compressor station is literally nothing, except that pumping is for liquids and the compressor station is for gases. And just like the oil pipeline, there is a block valve and metering. I'm not showing it here, but there are laterals for gas pipeline as well. The gas processing facility splits up the gas into various components. For example, methane will be either distributed through a distribution company. So this is where we get gas for our heating or taken to the industry, or it can be taken to an LNG terminal where it's liquefied and then sent over. Why liquefy and then send over anywhere? Why not just run a pipeline? The one very common reason would be that if some other country needs it, let's say such as Japan, because they're a consumer of LNG, there is no pipeline that can run from the US to Japan all the way, but you can liquefy it, put it in a ship, and the ship can take the LNG to Japan. The liquefaction of methane reduces the volume by about 600 times. So it's much easier to liquefy it and then ship over than simply compress. The gas processing facility also separates out propane, which is also needed, and then it's also shipped out. A10 and C4 plus chemicals, it generally would go to what's considered a petrochem facility, where it's used for making many products, and it's taken to smaller industries from there. Typically, anytime oil or gas is put inside a pipeline or is ready for transportation, that starts what we consider to be midstream. Anything prior to midstream is upstream, and similarly at the end of transportation is downstream, up to that point where the liquid or gas enters into a refinery or petrochem facility, it's all upstream. Refinery, petrochem is considered downstream. Some companies, especially those that work on the wells, such as Schlumberger, which are service providers for wells and well itself, they consider upstream to end here. By their definition, upstream literally ends the moment oil or gas leaves the Christmas tree. But mainly the definition that goes in the industry is upstream starts, upstream ends when transportation starts. Any questions here before I move on? Because I'm going to change topic a little bit. All right.
Yeah, I think this is great. This is an excellent overview. I've never had anybody explain the whole industry in one slide like this before. So excellent work with that.
Right. Good. So moving forward, of course, there's no single clean line such as the one that we're showing running from each well going all the way up to the end. Many wells, and US actually has approximately 800,000 producing wells right now, actually closer to 900,000 now. So they're all producing, and of course they all go into the same facility. Many of them, not the same, I'm sorry, many of them go to a single facility, such as, let's say, oil processing facility. Many oil processing facilities may go into a set of tanks. Many tanks and many facilities may be feeding into a single pipeline. And then many pipelines may end up going to the same refinery, or the pipeline may split into multiple refineries also. So this whole infrastructure that looks so clean, like John said in a single slide, is actually not clean at all. It actually is fairly messy. This messy. This is the pipeline infrastructure, only the pipeline infrastructure in the US. And as you would imagine, it's very well connected and very interdependent also. Some of you, if you were following what happened to the Colonial Pipeline some time ago, this pipeline running all the way from Houston, going all the way up to New York is the Colonial Pipeline. When this is it, when that failed, we saw what happened. The point was that it's all so well connected that one pipeline goes down, and the repercussions from that can be fairly large. We saw huge pipelines, and this picture is from, I think, New York, huge lines in front of gas stations. Similarly, a few wells going down in any one location can cause disruption in many other parts of that infrastructure of oil and gas pipeline. So it's important to realize that not only is each and every one of those facilities and processing facility, refinery, whatever it may be, is important, but the interconnectedness of that is also important because it can affect multiple other facilities at the same time. All right. So that was all science. I'd quickly like to actually touch on a couple of commercial aspects of it. We won't get into too much detail, but I'll touch on two things which will feed into our discussion coming up. So the first one, I'm going to call it barrels to dollars, because we can talk about barrels, we can talk about this technology and that technology and this particular facility and that facility. But really, it all finally has to end up in terms of dollars, because that is how businesses work. Now, US average production of oil right now is 10.75 million barrels per day. This is the effect of COVID. We were approximately 13 just before COVID. And COVID, we kind of came down. And since then, we have been going up a little bit, except for this last dip. This number is as of the previous week. Last week, approximately, we were making 10.75 million barrels per day. The price of oil right now, it changes literally every minute, every second. But right now, it's at $72 per barrel. I'm going to use a very approximate and rough number of $70 a barrel. That 10.75 million barrels a day at $70 a barrel translates into approximately $750 million per day of production only in the US. That's a very big number. This is just one day. Now consider just a single facility that's producing 100,000 barrels per day. That, by the way, would be a relatively large facility. Typical facilities, you can assume, are around 10,000 barrels a day. I'm picking up a relatively large facility. At $70 a barrel, this comes out to be $7 million per day, or approximately $300,000, I'm sorry, per hour. That is how much a typical facility of that size is producing. The reason I say that is that at that kind of money being made every hour, nobody wants a shutdown of their facility. These oil and gas facilities are made to run 24/7. They don't stop. Refineries and some of the larger facilities that are making that kind of money, or even more sometimes per day, per hour, they do not want to shut down even for a single hour. Their shutdowns are literally once in 5 years kind of shutdown, and they're planned well in advance. And they spend literally millions of dollars planning what to do in that shutdown. Important thing right here is that oil and gas facilities, especially if they're large or even largish, they don't want a shutdown. It's a fairly big no-no in the oil and gas industry. That's an opportunity, by the way, and I'll get back to it, why I say that's an opportunity for people like us. The second is efficiency improvement. I'm going to pick up the same facility that's making 100,000 barrels a day, which is about $7 million per day. That's not the money they're making, actually, because they end up spending quite a lot of money in producing that oil and gas. Typically, the margins are around 10%, which is to say that of the $7 million they're making every day, they actually have to spend $6.3 million approximately to produce that 10,000 barrels a day. That's still plenty of money. Don't get into the detail of this table, but let's look at just a base case, which is to say that when they're producing 10,000 barrels a day, which is 7 million barrels per day, they're actually making about $700K of margin, which is money in their pocket. This 10%, by the way, is fairly typical of oil and gas industries. Some are as low as 3-4%. Some larger or more efficient companies make more than 10%. I use 10% as a typical average because it's a good round number. Let's say if you were to come up with a system that could improve the efficiency of the whole facility by just 0.1%, only 0.1%. The production goes up from 100,000 barrels to 100.1 thousand barrels. That translates into another $7,000 made every day, which is $2.5 million additional that goes into the pocket of that particular company per year. That is nothing anybody would scoff on. 0.1% increase in efficiency translating into $2.5 million per year, going straight to the pocket of the company. So the reason I said this was a potential opportunity, both of these, is that even though these, again, like I said, shutdown is a no-no and efficiency is difficult to achieve, 1% efficiency improvement is a big deal. Right now, many of these facilities are running so efficiently at the moment that getting a 0.1% improved efficiency from the whole facility is a big deal. It's not easy. It's difficult to achieve. But if you could do it, there's money to be had because you're telling the customer, I'm going to give you something that will allow you to make $2.5 million extra per year. So they probably will be willing to pay you something for it. So opportunity for analytics, which is what I wanted to get into. But before I go there, any questions about what we have discussed?
Yeah, can I ask a question?
Sure.
So my question is, so you've assumed here gross margin at 10%, but I assume that there are fixed costs so that when the price of oil fluctuates, that their profitability changes pretty drastically. Could you talk about that a little bit? Do you know much about that?
Yes, so let me touch on that, but no, I won't go into too much detail because there's plenty of detail around the gross margin. So of course, the cost has two components. There's a fixed cost. And to give you an example, to drill a new well in Permian onshore, let's say costs about $10 million. A company probably gets money from the bank or loans the money or gets it from an investor, $10 million to drill that well, but now they have to repay whether or not they're producing. So that cost becomes a fixed cost. But then there are some operating costs also, such as maybe an operator who's working on the well or on that facility. If the well is not producing for whatever reason, they can say, hey, operator, we don't need you today. You don't have to come. That cost is directly related to whether or not the well is producing. The company can choose whether or not they want to produce from that particular well or not, depending on the price of the well that particular day. It's not an easy decision though, because not producing means that they still are paying the fixed cost and they have to make a decision on whether they don't produce, kind of keep their oil for later production. It's called deferred production, or they keep producing and make maybe even no money or sometimes even negative, but keep going. Stopping many of these facilities and then restarting them also has a cost to it. So the decision to stop or not based on the price of the oil that particular day is difficult. And very rarely do companies make a decision on a daily, weekly, or even on a monthly basis on whether or not to stop production from a given facility. There's plenty to it, by the way. Your question is very good, but it's complex enough that I cannot get into a whole lot of detail in today's discussion.
Thank you, that was great.
All right, so I'm going to talk about a few examples or applications, I would say, where data analytics can be applicable or can be used for maybe that 0.1% of increased efficiency or some kind of a commercial impact. So important thing here, even if you have a wonderful formula and a wonderful algorithm that can work perfectly, if you cannot easily translate that into how will the company make extra money from it on a daily, weekly, monthly basis, it won't fly. So whatever you do, have a business plan around it that says, this is how you'll save money, Mr. Customer or Miss Customer, and only then it'll fly. All right, so you've probably seen this structure along many US highways. It's called, by various names, some people call it pump jack, some people call it rod pump, some people call it by different names. What this is doing is it's pumping oil from the well, and generally this is used for wells that are not producing a whole lot. A typical good well, offshore well, produces, let's say a good one, produces, let's say 5,000 barrels a day. Many of these pumps that have these rod pumps on them, they're producing of the order of 10 barrels a day, sometimes even lesser. They may be somewhere between 10 and 100 barrels a day, but they're not producing a whole lot. You probably also notice that as you go along the highway, many of these are not working. They're supposed to go up and down, as they pull oil from the well. But if you've seen some of these, many of these you would see they're stopped, they're not working. It seems that they've stopped working for whatever reason. It's not that they're stopped for good or they have been scrapped. The way these work is they actually work for a while and then they have to stop to wait for something to happen and then restart. And this is what they're doing. Again, this actually is many thousand feet down the well. It's another completely off-scale picture, but that's the pump itself. And this beam is actually running this pump. And what the pump is doing is it takes oil or gas or what, oh, not gas, oil from the well, and it pushes it up. That's the idea in this pump. So the way this works is that as it goes up and down, it pulls liquid from under this valve and pushes it up. Takes the liquid from under this valve on each downstroke of the beam and pushes it up on each upstroke of the beam. And that's how oil flows up. What happens sometimes though, is that it keeps pushing oil up. There is no more oil left in the well itself because the well is not flowing enough oil from the reservoir into the well. When that happens, the pump has to run dry, and that's not a good thing for the pump. So there's instrumentation up here that senses that and says, oh, it's running dry, and it stops the pump. Right now, what's happening is that it stops the pump for, let's say, an hour, a couple of hours, and wait for oil to flow back into the well from the reservoir, fill up a little bit, and they assume that after X hours or X minutes, it will be filled up again, and then they restart the pump. And then if they have enough data, they can say, yeah, after 1 day, I'm going to stop anyway. And after 2 hours of stoppage, I'm going to restart. That's how it's working right now. That's, of course, not the best way to do it because that's very inefficient. This is a good application of data analytics where you can literally sense when the well is drying up and then restart as soon as you can restart. So the problem statement becomes, when is the latest you can or you should stop? And when is the earliest you can restart? So the pump is stopped for the least amount of time. When the pump is stopped, it's not being used, it's not being productive. And industrial parlance will say it's not an efficient use of that asset. To use that asset efficiently, we need for it to be running for as long as it can run. So this is what you need to do. I'm actually not going to get into too much detail on how the analytics would work. I'll leave that up to you. But consider what can you do. It's actually a relatively easy problem in the sense that there aren't a whole lot of variables. And if you had the right instrumentation, you could actually, maybe with 10, 15 different variables, you could come up with a good data analytics algorithm to figure out what's the best time to stop and then what's the best time to start. But there are other constraints that you need to take into account, and these are all commercial constraints. Remember, I said that this pump is producing only about, let's say, 10 barrels a day. If you were to come up with something that either takes or requires more instrumentation, or a lot of computation, or edge connectivity, or any upfront cost that's too high, where the return will take just too long for the customer, they may say no. So the trick here is not just that, but also what is the available instrumentation? And if you do want any extra instrumentation, how much would that cost? And how much increased efficiency will that additional cost bring in? And the fact that if your computation needs a lot of computational power, will that be additional cost that you'll have to put right at the well? So I would consider this to be a relatively easy analytics problem, but a relatively difficult techno-commercial problem. So as you look into opportunities such as this, think of it not only from how can I technically solve it, but also will it be viable also or not? John, how much time do we have? Another 5-10 minutes?
Yeah, we have about another 5 to 10 minutes, and then we'd like to save a little bit of time for questions.
All right, I have two more examples. That's a little bit more complex one. So again, remember that pipeline we were talking about and that whole infrastructure, and I was saying this pipeline could be, let's say, 1,000 miles long. The total Colonial Pipeline length of the pipeline system, so not just the main segment, but the main segment and any laterals that were coming in or going out from it, is approximately 5,500 miles. Yeah, so divide that, it's an oil pipeline, right? So divide that by approximately 25 to see how many pumping stations are on it, and by approximately 5 to see how many valve stations are on it. Thousands and thousands of them, right? And they're out there somewhere, who knows where. The operator, Colonial Pipeline in this case, in this example, they want to see what's happening on the pipeline. And of course, they cannot have somebody run along the pipeline or a plane that goes along the pipeline to see what's happening. There is some infrastructure, like I said before, on each one of those valve stations, and plenty on each one of those pumping stations, and any metering stations that may be on there. But that's still out there somewhere. It needs to be brought back in. Sorry about this small diagram, but the intent is not really this diagram. The idea here is that whether these are valves or pumping stations on the pipeline, or these are wells that are out there somewhere where the end user wants to get the data, all of that data has to travel from wherever it is geographically spread out into a central control room where somebody can sit and take a look at. It's actually, that technology is not difficult. It exists. It's called a SCADA system. It can bring in data from wherever it is, not an issue. The issue these days is that as the data is coming in from all of those different locations, there's a pretty elaborate infrastructure of networks, IT infrastructure, that is required to pull that data in at fairly decent bandwidth and data update rates and bring it back into a central location where somebody can actually look at the whole facility or the whole structure, infrastructure along the pipeline and any facilities. That poses a problem. And the problem is this: it works well and it has been working, except that when somebody says, let me see if I can get into that infrastructure and try to bring it down because I want some of those Bitcoins, right? That's exactly what happened in Colonial Pipeline. And they go out literally in the middle of nowhere where there is a small block valve on the pipeline. There's nobody around. It literally is in the middle of nowhere. Nobody's watching. They go on there. There's a small switch there because this data has to go through a switch before it goes to the central control room. They hook their laptop and then try to figure out how they can get into the network. And once in a while they do. And when that happens, Colonial Pipeline goes down for 5 days. So the issue right now is, how can I have all of this working while making sure that we can detect an intrusion as quickly as possible, preferably when it's happening? This is a difficult and probably one of the most difficult, or amongst the most difficult problems. This is a cybersecurity issue. Intrusion detection is only one way to stop it, but that's stopping it right as it's happening. It's not easy. Is there an opportunity for data analytics to work here? Absolutely, but it's going to be a tough one. Essentially, what you need here is a big network, and when I say network, I mean in data analytics term, is this PLC, which is to say a controller, a data gatherer, is it required to speak to this web server? Is this one required to speak to this particular local HMI? This is a network which says, is this partner required to talk to this partner? What should be the data flow? Should it flow only one way or the other way? What is the protocol of that data transfer? This becomes a huge matrix of not only relationship, direction of data, but what language or what protocol they're talking, what frequency, how much bandwidth, how often they talk, what kind of data they transfer. If you could get all of that together and come up with an algo that detects whenever somebody goes to this particular valve and hook up their laptop and for the first time pushes in a ping, which was never supposed to happen on that network, and you can find it and locate it, That's a very good business case for many companies. Like I said, this is not an easy problem to solve at all, especially on a large network, but it can be solved on relatively smaller networks, which had, let's say, only 50 devices. Still difficult, but can be done. This, by the way, is not just oil and gas specific, but given the importance of oil and gas for any country, this is definitely needed, not only from an efficiency perspective, but also almost from the security perspective of the country. All right. One other final example. We talked about no shutdown, but shutdowns do happen. Even for a small facility, which is producing 20,000 barrels, so I'm down from the 100,000 that I previously had to only 20K barrels, is producing $1.4 million a day, and a margin, which is money in the pocket, of 140K a day. Even at this kind of money making, nobody wants a shutdown. This is that facility, and you're probably more used to seeing something like this, which is a process flow diagram, which says this is where the wells are, they go into a separator, and then other stuff happens. But the customer or the owner or the operator of this facility would like for this to keep working 24/7 and never shut down. But they do shut down, obviously. This one well is not producing, or there's a big slug that comes in, which is, say, a big rush of oil or gas comes in, and this separator cannot handle it, or whatever the case may be, and then the facility can or has to be shut down. If you could find a way to look at this facility as a whole and predict a shutdown, and even better, also suggest how to prevent that shutdown, that's a golden algorithm to be sold to many of these facilities. It'll sell like hotcakes. It's not easy because the number of points, data points here is pretty big, and the relationships are pretty complex. But then this is also a very good example of the kind of problem where a data-based model and a physics-based model can work hand in hand to come up with an algorithm that can predict a shutdown. Predicting, actually, even though it's not easy at all, it's not as difficult as saying, what can you do, operator, to prevent that imminent shutdown? That's an even more difficult problem. So basically a prescription, or at least a suggestion, to say that's how you can prevent it. I'm going to stop here. Actually, this was the last slide. I'm going to skip the summary for now, and you'll get these references when you get a copy of the slide show, and I'm going to stop here on that diagram to kind of poke your brain for more questions.
Fantastic, Aasim. Well, thank you so much for that presentation. We're going to open it up now for questions from the audience, and you can do that in one of two ways. You can either unmute your microphone, or you can put something in the chat window, and I'll be monitoring the chat window. So Aasim, I think this was a great overview. You gave a great overview of the oil and gas industry, including the upstream, midstream, and downstream areas. And then you had 3 motivating case studies for data analytics, showing some of the economics behind it, what's driving some of those, including just increasing production, cybersecurity that prevents shutdowns, and then also predictive methods to anticipate shutdowns, potentially save the unit. And along with that, like predictive maintenance on equipment, which is very big on pumps and other things, as you know. So just a question for you. I know that with data analytics, there are many people also proposing many different solutions out there, and so in some ways the space is a little bit not necessarily crowded, but the number of people that give you details about what they're doing and what's underneath the hood with their algorithms is sometimes a little bit sparse. How do you approach that when you're dealing with customers? How much detail do you give about the data analytics that you're using, or do you focus mostly on the benefits?
John, that's a good question. And actually, that would depend really on the company, as in not me as an employee, but the policy of the company. Because the company will have a policy whether or not they want to open up their intellectual property to their customers. So both mindsets are possible. The companies who say we're not going to open up under the hood and show you what's under this algorithm, they don't want anybody to steal away their intellectual property. Versus somebody who does show all of that, they may have a benefit, but they may also have an issue where the IP can be stolen. And of course, it happens in the industry all the time. If I were to say something, especially for young entrepreneurs who don't necessarily belong to large corporations with these IP issues, is that the more you can explain to a customer about how your algorithm works and how the final benefits relate to that algorithm, the easier the sell becomes. So one way is to exactly do or convince a customer that this is not black magic. This is how it works. You can still kind of keep some of that intellectual property kind of under the hood, but as little as possible, and literally explain to them how this is working. It's probably an easier sell. The other way, which some other companies who do not want to open up their IP, is to say, let us just run a proof of concept for you. We're going to keep this black box as a black box, but at our cost, we'll come install it, but we'll let it run on one of your facilities, and we'll show you the benefits. And if they are able to demonstrate the benefits, then the customer may purchase it from them. Of course, producing it without necessarily any investment from the customer and then running it means that you have to incur that extra cost yourself. Like I said, for young entrepreneurs, it may be a little bit difficult. And that's why I think opening it up to a customer and showing at least some of the working of your algo may actually be useful and easier.
Fantastic. Well, let's take some time now for questions. If anybody would like to unmute your microphone. Looks like the classroom there has theirs unmuted. So Doug, are there any questions there in the classroom?
Scanning. Bunch of nervous looking students around, hoping I don't call them.
Well, I've got one more question for you, Aasim, while we're people are collecting their thoughts. One of the things I've heard recently from companies, and this surprised me, is that I've heard some people say that the data that we're collecting from reservoirs, from instrumentation, from other things, is becoming almost as valuable or more valuable than the oil in the ground. Do you agree with that? And what are your thoughts on that statement?
So John, the fact that it's becoming valuable, absolutely 100%. Is it becoming more valuable than the oil itself? I don't think so, not yet. It may become that valuable, but not yet. The reason it's becoming valuable is that once that data is available, we can use that data. And when I say we, I mean data analysts and scientists generally, to find better ways to extract more and more oil from those reservoirs. Typically, where we are right now, even though the technology has improved a lot, but even as we leave or stop production from a reservoir because we cannot produce from that reservoir, we are still leaving a fairly large percentage of oil in the ground, simply because we don't know how to get it and how to get it out of the ground. And when I say large, I mean of the order of 20, 30, 40%, depending on the geology of that particular reservoir. With data analytics, we can produce better, faster, and more from the same reservoir. So data from all of those activities that you mentioned is definitely becoming more and more important as we find more and more ways to convert that data into information and insights.
Fantastic. Great answer there. Okay, let's see. I have a question from the chat. Great presentation. In your experience, would you say that the main challenge for effective data analytics solutions is in algorithm development? For example, we need more sophisticated solutions, or in the implementation and scalability?
That's a very good question. It depends. And I know that's a weird way, but it does depend on various things. In some cases, it depends on the issue itself. In some cases, like we saw that rod pump, which is not necessarily very well connected, we do need an efficient algorithm that can run locally on a very small, cheap computer. So in this case, the computation requirement of the algorithm and the efficiency of the algorithm becomes important because in the case of rod pumps, it has to be cheap and it has to be local. Versus let's take another example where the connectivity is wonderful, as is generally the case on a pipeline, and all the data is going into the cloud already on a central location. And all you have to do is move it into the cloud. Once the data is in the cloud, computation power is lesser of an issue. You can design an algorithm that is huge, can take thousands and thousands worth of records and variables into account, and can run a huge algorithm maybe once a day to come up with some good, important KPIs and set points for the pipeline. In that case, the algorithm doesn't have to be super efficient, but it needs to be able to take care of a lot of that data. Computation requirement becomes lesser of an issue. So in that case, necessarily the efficiency of the algorithm is not as important as just its ability to handle all of that and producing a result that is useful.
Oh, fantastic.
Interestingly enough, to add to that, in many cases, because a lot of these oil and gas facilities have good automation systems in place, except for the reservoir, because I'm not very aware of that, but from those automation systems, data that is available is relatively clean. So the majority of the data that we see, especially manually entered data, needs to be cleaned up quite a bit. But from a good automation system that has been designed from the perspective of to be used later from data analytics perspective, produces fairly clean data. So a lot of that time that we spend in just cleaning the data is not necessary, or it gets reduced by a big margin.
Great. Well, Aasim, thank you so much for your presentation and the questions. This has been very insightful, both from an overview standpoint, but also some very specific case studies on data analytics and how they can be applied. I appreciate your perspective, especially with the many years of industrial experience, but also the inspiring methods that you've taken to continuously learn and improve. So thank you so much for
John,
that.
thank you for having me.
Okay.
The hand. Let's go ahead, everybody.
Thank you.
All right. Well,
All right.
thanks, Aasim. We'll go ahead and stop the recording now and then and log off.
All right. Thank you.